So what if our entire map of the universe, everything we think we know, is based on ideas we can't actually prove? Today, we're diving into a pretty radical new vision of the cosmos, one that basically throws out the old rulebook and starts with a really simple, powerful premise. Trust only what we can see.
I know, it's a huge question, right? Is our map of the universe fundamentally wrong? For decades now, we've had this standard model that's been our guide. But what if, just what if, that guide has been leading us just a little bit astray?
You see, our current understanding of the universe, the standard model of cosmology, it's been incredibly successful. It's explained so much. But lately, as our instruments have gotten more and more precise, we're starting to see some pretty serious cracks in that beautiful foundation.
Okay, so this shows the two biggest puzzles that are giving scientists some serious headaches. First, there's the Hubble tension. Put simply, when we measure how fast the universe is expanding right here, right now, the number we get just doesn't match what our theories predict based on how the early universe looked. They just don't line up. And then there's the S8 tension. The universe today is, well, it's a bit smoother and less clumpy with matter than our models say it ought to be. And look, these aren't just small rounding errors. They are major disagreements that really hint at a deep, fundamental problem with how we think the universe works.
So, to really get a handle on the problem, we've got to look at what our current model is actually built on. You can think of it like a massive, grand empire. And like any empire, it stands on a few key pillars, or, in this case, a few key assumptions. So our standard model is built on four really huge ideas. This idea of an infinitely dense starting point, a mind-bogglingly rapid inflation phase right at the beginning, a mysterious cosmological constant that acts like anti-gravity, and of course, a super hot Big Bang. But here's the kicker, the really critical part that this slide is pointing out. We have never, ever directly observed any of them. They are brilliant, powerful theories that explain a lot. But at their core, they are still assumptions we've inherited. And this is where this new framework comes into play. It suggests that to fix the cracks, we can't just keep patching the old building. No, we have to start completely from scratch with a totally different blueprint. The philosophy here is really simple, but it's also pretty profound. Instead of trying to force all this new, weird data into our old theories, this new approach just says, let's stop. Let's break the chain. Let's get rid of those legacy assumptions. It tries to build a model right from the ground up, using only first principles, and then test it against the only thing that really matters, the raw, unfiltered data coming from our telescopes. And here is the central idea, and it's a wild one. This model proposes that our four-dimensional universe, that's 3 dimensions of space plus time, is essentially a shadow. Just imagine a really complex 3D object casting a simple 2D shadow on a wall. Well, this theory suggests our entire reality is a 4D shadow that's being projected from a much more fundamental, timeless, 5-dimensional reality. Everything we see and experience, from galaxies to gravity, is just a feature of that projection. So how in the world do you test an idea like that? Well, the process is brilliantly, ruthlessly simple. Step 1. You start with the core principles of this 5D framework. Step 2. You use those principles to derive specific mathematical predictions about what our telescopes should be seeing. And then step 3, the most important step of all, you compare those predictions directly to the raw data. No tweaks, no adjustments, no fudging the numbers. The data, and only the data, gets to be the judge. Okay, so does this radically different picture of reality actually work? I mean, does it hold up? Well, let's see how it tackles those big cosmic puzzles we started with, because honestly, the solutions it offers are pretty fascinating.
First up, dark matter. So that dotted line on the graph shows how fast stars should be rotating based on all the stuff we can see. The solid line is how fast they're actually going. Way too fast. The standard model solution? Invent an invisible particle to explain the gap. This new framework says, nope, you don't need a new particle at all. That extra gravity is simply an effect of the projection's geometry, a kind of shadow gravity that it calls S-matter.
Next up, the Hubble tension. Remember that big disagreement in the expansion rate? Well, get this. This framework actually predicts it. It calculates that we just happen to live in a relatively empty patch of the cosmic web, a void, which should be expanding about 8 to 12% faster than the cosmic average. So the tension isn't a conflict in the data. It's the expected result of our specific address in the universe. It's not an oops, it's an aha.
And what about that clumpiness problem, the SA tension? Well, the standard model, on the left, builds structures from the bottom up. Small things clump together to form bigger and bigger things. This new framework says it works the other way around, top down.
The fundamental geometry of that 5D projection creates the massive cosmic web first, and that web then dictates where the galaxies form. And this top-down process naturally leads to a smoother, less clumpy universe, which is exactly what we observe.
Now this is really exciting. The very latest data, some of it hot off the presses, is hinting that dark energy isn't a constant force. It looks like it might actually be changing over time, and that's a huge problem for the standard model. But for this projection framework, that's exactly what it predicts. Its model of energy flowing into our universe, almost like a hydraulic system, perfectly matches this new, evolving behavior we're just starting to see. And this right here, this might just be the mic drop moment. You see, the standard model has to invent a cosmological constant and then fine-tune it perfectly just to make the math fit the data we see. But this framework, it calculates the value from its own first principles, from the basic physics of its 5D energy flow. And the result it gets, it matches our observed reality with incredible precision. That isn't a patch to fix a theory, it's a core prediction. Okay, so explaining things we can already see, that's impressive for sure. But the true test of any great scientific theory, the thing that separates the contenders from the pretenders, is whether it can predict something new, something we can actually go out and look for. You know, for any new theory to be taken seriously, it's got to do three things. It has to be logically sound without contradicting itself. It needs to simplify things, explaining a whole bunch of puzzles with one core idea. And, most importantly, it has to stick its neck out and make new, testable predictions that could actually prove it wrong. And this framework makes some very specific ones. It predicts that the new square-kilometer array telescope is going to find a minimum floor of hydrogen gas in cosmic voids, that no void will ever be completely empty. It also predicts that the Euclid and Webb telescopes will see an enhanced rate of duplicated galaxy images, a really strange gravitational lensing effect caused by the projection's geometry. These aren't vague ideas, they are hard numbers. The theory has put its cards on the table.
So, after all of this, what does it all mean? Well, whether this specific framework turns out to be right or wrong, its whole approach points to a much deeper truth about how science actually moves forward.
I mean, this has been the story of science throughout history. Every great leap, from realizing the Earth revolves around the sun to Einstein's relativity, didn't come from just patching up the old map. It came from someone having the courage to look at the facts, to see that they just didn't fit, and to then draw a completely new map of reality. And that leaves us with one last thought. We've just walked through a really challenging, really different idea, one that asks us to question the very foundations of our cosmic model. And whether this specific theory is right or wrong, its method is a powerful reminder of the core principle of science. It leaves us with a simple but profound question. What happens when we finally have the courage to let the data speak for itself?